Hello, I am Jonathan Hasenburg. I'm a PhD student at the Mobile Cloud Computing Research Group at Einstein Center, Digital Future and Technische Universität Berlin. In the next couple of minutes, I will give you a high-level overview on our paper Managing Latency and Access Data Dissemination in Fog-based Publish-Subscribe Systems. Let's start with a description of the state of the art. To realize asynchronous, loosely coupled communication between a large number of IoT devices, widely used systems such as Amazon Web Services IoT or Google Cloud IoT build upon topic-based publish-subscribe. Pub-subsystems are generally beneficial as they are payload agnostic and facilitate communication between end devices that do not even have to know each other. These systems, however, usually run in cloud environments, which leads to higher latency than many IoT applications can tolerate. The emerging fog computing paradigm promises low latency while also keeping the scalability aspects of the cloud. For latency, application components are deployed close to or at the edge. For higher scalability, they are deployed in or near the cloud. To make topic-based pub subsystems fog-ready, we propose to geo-distribute worker instances across edge resources in a way that individual messages of local end devices can be delivered with low latency. Especially in global deployments, the number of edge brokers can quickly increase to thousands of individual instances. All these brokers have to be interconnected. This is needed to deliver messages to subscribed end devices independent of the broker at which it has created a subscription. There are two general strategies for message distribution between the broker instances. First, broadcasting messages directly to all brokers. We call this global flooding. Second, a cloud instance forwards messages from and to edge brokers. We call this cloud relay. With global flooding, communication latency is optimal and mobile end devices can create their subscription at any broker to immediately receive matching messages. With cloud relay, edge brokers forward the messages and subscription to a central cloud broker, which uses the subscription information to decide where to forward the messages. While minimizing excess data dissemination, this increases latency. From this, one can easily see that there's a trade-off between latency and excess data dissemination. To balance this trade-off, we propose to build and use broadcast groups. The main idea behind our broadcast groups approach is to split the set of edge brokers into well-connected groups, which use flooding for intra-group communication and a cloud relay for intergroup communication. For example, if the member broker M1 receives an event from a local client, it broadcasts it to the member broker M2 and M3, as well as to the leader broker L1. Every broker can then immediately match the event against subscriptions created by local clients. The leader broker also has a special task to forward the event to the cloud broker C. Other leader brokers will have created subscriptions on behalf of the members at this cloud broker too. Thus, the cloud broker can then decide which broadcast groups require the event that was originally received by member broker M1 and distribute it accordingly to the leaders. Leaders that receive a message from the cloud broker then also broadcast the message to the member brokers in the group. Our approach minimizes communication latency at the edge. This is particularly important as low latency communication is often required by end devices in close physical proximity. As a side effect, flooding also handles frequently updated subscriptions of mobile end devices particularly well, as messages are sent preemptively to all brokers at which an end device could create its subscriptions. We developed a dynamic broadcast group and redirection process. The key idea is that brokers whose communication latency is below a given latency threshold are in the same group. The whole process is, however, a lot more complex. You can find more information on this in the paper. We evaluated the overheads of the group formation process through simulations. In particular, we tried to answer two questions. First, how does the latency threshold influence the total number of broadcast groups? Second, how does the latency threshold influence the number of messages needed to complete the process? In the simulation, brokers are distributed across the globe. We used a public data set of major cities as a source for realistic broker locations. Regarding the first question, we can see that increasing the latency threshold decreases the total number of broadcast groups quadratically. Please note the logarithmic scales in the figure. In addition, the total number of brokers does not influence the number of broadcast groups. This confirms the effectiveness and scalability of our threshold-based approach, as fewer broadcast groups mean that, on average, each group comprises more members. Regarding the second question, one can see that the number of group join operations needed to reach a stable state scales linearly with the number of brokers, and this is also the case for different latency thresholds. Therefore, the overhead of the group formation is On. The number of joins is a lot higher than the number of brokers, as brokers examine different broadcast group options throughout the process. When they found a local optimum, the process reaches the stable state. The figure is quite complex, so you might want to pause the video to examine it in detail. Besides the simulation experiments, we also ran experiments with the prototypical implementation of our approach. Our prototype is an extension of the popular MQTT broker Moquette. We only added the features necessary for a proposed broadcast group approach, so our prototype is fully compatible with other vanilla MQTT-based pub subsystems. If you're interested and want to set it up yourself, feel free to visit our GitHub repository. The evaluation scenario is a simplified Internet of Vehicles use case with three types of clients: cars, monitoring equipment, and traffic authorities. For improved driving safety, cars exchange telemetry data with other cars so that they know when cars brake or change lanes. The monitoring equipment, for example a camera, collects traffic information that it sends to the traffic authority for processing. In the following, we only concentrate on the car telemetry data exchange. Details on the monitoring equipment data exchange can be found in the paper. When running the scenario workload, we can see that the latency of messages received by cars is similar for the global flooding and the broadcast group strategy. We call this latency the message delivery latency. For both strategies, 50% of the messages received by car 2 and car 3 have a latency of about 4 milliseconds, as the corresponding messages can be matched at edge broker 3 directly, and the one-way latency between edge broker 3 and each car is 2 milliseconds. The remaining 50% of the messages received by car 2 and car 3, as well as all messages received by car 1, have a message delivery latency of about 7 milliseconds. And the messages are additionally sent via the link between edge broker 2 and edge broker 3. The cloud relay strategy performs significantly worse. While 50% of the messages received by car 2 and car 3 have a similar message delivery latency as in the global flooding or broadcast group experiment, the remaining 50% of the received messages, as well as all messages received by car 1, are routed via the cloud. This leads to a message delivery latency of 55 milliseconds or higher. For a more thorough analysis of message latencies, we refer to our paper. To determine the amount of access data of each strategy, we logged each message processed by every broker and determined the amount of correct and redundant messages. Correct messages are messages processed by brokers that either have a matching subscriber or to which the publishing client is connected. redundant messages are all other messages processed by workers. These messages have to be discarded and are therefore counted as excess data. From the numbers, we can see that the broadcast group strategy leads to a similar amount of excess data as Cloud Relay, while global flooding performs worse. To wrap things up, I will now summarize our contributions and findings. We described the latency and excess data dissemination trade-off that needs to be taken into account by geo-distributed pub subsystems running in the fog. Then, we proposed a solution that relies on dynamically sized broadcast groups to manage this trade-off. Broadcast groups split the set of edge brokers into well-connected groups. We choose flooding for intra-group communication and the crowd relay for inter-group communication. This minimizes communication latency and copes well with frequently updated subscriptions and mobile end devices. We evaluated our approach through simulation and experiments. Our results confirm the effectiveness of our approach and that involved overheads remain manageable. This even applies to global deployments, with thousands of individual broker instances.